In this screencast, we're going to focus on finding eigenvalues and eigenvectors of a 3x3 matrix. Our matrix, 2, 1, 4, 1, 2, 4, 0, 0, 1 is the matrix we're going to look at. The first thing we do is find the eigenvalues. To do that, we subtract lambda from each of the entries on the diagonal. So we get a 2 minus lambda 4, 0, 0, 1 minus lambda. Now, I need to find the determinant. To get the determinant, I'm going to use the bottom row. The reason why is then I can utilize the two zeros as part of my cofactor expansion. I write them down and I have to determine the sign. So we start here, plus, minus, plus, minus, plus. I can ignore the determinants I need here, but I now have to include the matrix found by removing the row and column containing the 1 minus lambda. So I have a 2 minus lambda, 1, 1, 2 minus lambda. Alright, we continue going. We've got a 1 minus lambda, and then here the determinant is 2 minus lambda squared minus 1. If we continue expanding, we'll have a 1 minus lambda. This is 4 minus 4 lambda plus lambda squared minus 1. Now, don't multiply through. This is already factored. So at this point, we'll just write this as 1 minus lambda. And let's just try and factor this. We've got a lambda squared. We have a minus 4 lambda, and a 4 minus 1 is plus 3. Well, that factors as 1 minus lambda. And then we have a lambda minus 3 and a lambda minus 1, which means 1, 3, and 1 are our eigenvalues. So lambda is 1, lambda is 3. This one has multiplicity 2, and we'll discover what that means as we go. We're now going to focus on finding the eigenvectors. Let's start with lambda equals 1. To get the eigenvectors, we take our matrix here, and we actually replace each of the lambdas with the eigenvalues. So 2 minus 1 is 1, 1, 4, 1, 1, 4, 0, 0, 0. Augment by 0, and now I need to reduce. If I put this matrix in reduced row echelon form, we end up with, well, the second row is the same as the first, so if I subtract them, I just cancel the second row, and everything is zeros except for the first row. I can now write this in terms of a system. We've got x1 plus x2 plus 4x3 is 0. We also have x2 and x3 are both free variables, so I'll include an equation that says x2 is x2 and x3 is x3. I'm going to rewrite that now as x1 is negative x2 minus 4x3, x2 is x2, and x3 is x3. We can write that in vector form as x1, x2, x3 equals, well, there's some things that are times by x2. We've got a negative 1, a 1, and there's no x2 here, so 0. We also have some things times by x3. There's a negative 4, no x3s there, and 1 x3 here, which means that the eigenvectors are non-zero linear combinations of the two vectors negative 1, 1, 0 and negative 4, 0, 1. There's infinitely many of them, and these two vectors, which are linearly independent, span an entire plane. So there's an entire plane full of eigenvectors in this case. Now we need to look at the last example, when lambda is 3. If lambda is 3, we subtract 3 from the diagonals, giving us a minus 1, 1, 4, 1, minus 1, 4, 0, 0, minus 2. We augment by 0, and then we reduce. So if I'm going to reduce the thing, first we're going to have to take row 1, or row 2 plus row 1, and that'll help us with the first. We got a negative 1, 1, 4, 0, 0, 0. That'll turn into an 8, 0, and then 0, 0, negative 2, 0. Let's take row 1 and times it by negative 1. We'll take row 2 over 8, and we'll take row 3 over negative 2. Notice that these are going to end up being the same, so I could just cancel the bottom row to start with. And I'm left with 1, negative 1, 4, 0, 0, 1, 0, 0, 0, and I'll put the zeros on at the right now. Okay, so now if I want to remove the 4, I end up doing row 1 minus 4 row 2, and that'll just put a 0 there. So my final RREF form involves that. The only free variable in this case is the second column. So x2 is free, but x1 minus x2 is 0. x2 is free, and x3 is 0. I can rewrite this top one as x1 is x2, rewrite it in terms of the free variables, and then we get x1, x2, x3 is x2, x2, 0, which is x2 times 1, 1, 0. In this case, any linear combination of 1, 1, 0 is an eigenvector for lambda equals 3. So the vector 1, 1, 0 times any number at all, other than 0, will give me another eigenvector. So we have our eigenvectors for lambda equaling 1, we have our eigenvector for lambda equals 3, and that completes the screencast.